This lecture is going to be on hydrology and streamflow, that we will be measuring the volume of flow of a river that we call streamflow. Now, it's important that we can see the river from, say, a bird's eye view from above and from a cross-sectional view as if we were fish looking into the water. And this is what picture from class, making sure that we are calculating and measuring streamflow correctly. Maps show physical features, like rivers. We are a part of, or DHS is located within the upper Mississippi River watershed. The water flowing into the Middle Fork River eventually makes its way to the Mississippi River and into the Gulf of Mexico. The Mississippi River is a tributary to a larger river, right, the Illinois River. And the Illinois River is what flows into the Mississippi River downstream. We're going to call this stream order, that the Middle Fork River is simply a smaller river and it's going to have a small number associated with it. We're going to call this stream order. More on that shortly. So where is the Middle Fork River in the grand hydrologic scheme? Well, the Middle Fork River is but a tributary to the north branch of the Chicago River. And the Chicago River actually flows into along the Sanitary and Ship Canal, which is SSC, primarily to divert E. coli from entering Lake Michigan. So here at Deerfield, we are located right here. We are along the Middle Fork. East of us is the Skokie River, and west of us is the West Fork. That these three come together and eventually merge into the North Branch, or in this case, into the Chicago River. Eventually, they merge into the Sanitary and Ship Canal, and it flows towards or into the Illinois River, and eventually the Illinois empties into the Mississippi River. We can look at this in terms of stream order and stream flow, that smaller streams have smaller numbers. The Middle Fork River is considered to be a primary stream, number one stream order. As streams merge at confluences, stream numbers get larger. It should be obvious that the Mississippi River has a large stream order number as many rivers flow into it. As streams flow downstream, they carry larger volume, right? The amount of water moving increases. Thus, stream flow increases as more moving water flows. So stream flow, we found, is width times depth times velocity. So stream flow, also called discharge, is the flow of water in streams and river channels and is a major element in the water cycle. It involves runoff of water from the land within the watershed to the bodies of water in the low-lying land. Water flowing in channels comes from the surface runoff from the adjacent land that is higher in elevation than the body of water it runs into. Gravity is the driver of the water's motion. And we can measure stream flow manually, which is how we will begin the year in this class, but is generally measured using gauges and technology. The recording of stream flow over time is called a hydrograph. Flooding occurs when the volume of water exceeds the capacity of the channel. So below is a hydrograph of rainfall of an area. And where you get this base flow is kind of the average flow here. But when you get these peaks, it implies that there was a rainfall event. That when you see these peaks, we're implying that there must have been some type of flood or flood stage where the river itself actually was too much for the channel itself. It exceeded the capacity of the channel. So here's a picture of it. Here's a picture of a flooded Mississippi River at some point, and I don't have the year for that. But notice, we can actually view it from this aerial photo. So stream flow is the volumetric flow. That stream flow, also discharge, is measured by measuring the width, the depth, and the stream velocity. That the width and the depth is a cross-sectional area. So we would say that the width would be how wide the river is, and the depth would be the average depths of these. That's an area, so a cross-sectional area. So area times velocity is going to give us a value of stream flow, or discharge. That we will be measuring the stream flow in the Middle Fork River. And we'll simply be measuring the width, the depths, and the velocity. And we can multiply them together and get a value in cubic meters per second. In this day and age of technology, we use remote sensing devices. That in this case, here's an acoustic Doppler current profiler mounted to a small watercraft that's used to measure this. It uses acoustic sound beams, and it actually gets kind of a real-time data that we no longer have to be, right? Humans no longer have to be somewhere to get information at that location. That technology and remote sensing technologies provide information to scientists, whether hydrologists or engineers, who are surveying the changing conditions of the river. Well, our Middle Fork River consists of a pool and a riffle system. That riffles are shallower regions of a river channel where water moves faster, right? Greater velocity and turbulence. There are larger sediment found here, such as gravel and boulders. Rivers often alternate with pools, which are slower, calmer, deeper areas with fine-grained bottom deposits that we just call mud. In the picture below, you should observe that the different gradients, right? Here's a gentle slope, here's a steeper slope that we can call gradient. They have different gradients which drives the water to different speeds. The greater the mean gradient, the faster the water will travel. It's essentially flowing downhill at a greater rate. Rivers are rarely straight. Rivers meander with age. Young rivers have less bend to them. Older rivers have much greater bend or meander to them. The greater the age, the greater the sinuosity. So we're going to use a couple terms in here, right? Greater meander. That this would be relatively straight, right? Relatively, still bend, and we can see alternating pool and riffle systems. But this would be greater sinuosity, or greater, it'd be more sinuous. And also pool and riffle systems. So why do rivers meander with age? Well, this is a result of erosion and deposition. That moving water has kinetic energy. This energy can modify the land in which it encounters and erode it. It breaks it down and transports it. Eventually, everything that is eroded is deposited or left behind. So water on Earth's surface is constantly at work, sculpting and shaping the surface. Land is constantly being eroded, and later downstream creates new landforms. So we'll see here as the water is moving here, it's going to erode the outside of the bend, and it's going to deposit sediment on the inside of the bend. So notice, over time, it's going to erode more, and it's going to deposit more on the inside. As a result, we get a greater amount of meander over time. An oxbow lake is simply a structure that is an aging river where it has meandered so much that it cuts off part of the channel itself. So oxbow lakes are generally cut off sections of the river itself. So sinuosity. Some rivers have a large amount of meander, right? Big meanders. This would be highly sinuous or high sinuosity. And rivers that flow out of mountains generally have much, let's just say, small meanders. They have a high gradient, right? A steep slope, and they have coarse substrates. So when we talk about substrates, that's important. A substrate is a substance or layer that underlies something or in which processes occur. So where a river exists determines its shape and structure. Rivers on mountains look dramatically different than rivers flowing over a low gradient land. So rivers and flooding. So we have what we call a floodplain. A floodplain is the plain in which a flooded river would actually naturally flow into. Once it exceeds the capacity, it's going to flow around the outside of it, and it's going to leave sediment behind. And this is simply a function of runoff. When precipitation reaches the land, it's going to flow from a higher elevation to lower elevation, so water is diverted or driven by gravity into the channel itself. At a certain point, it reaches capacity and it floods. Here we can see, here's a picture of an oxbow lake here. It's been cut off completely from the river itself. So rivers carry sediment. Gravel and sand, larger sediment, is dragged, rolled, and bounced along the bottom of a river. This is called bed load. These particles get rounded off as they are transported. Finer or smaller sand and mud are transported by the kinetic energy. The moving energy in water is called a suspended load. And lastly, some minerals are dissolved in the water and are chemically a part of the river itself. So we have bed load, suspended load, and dissolved load. And you can watch this animation. I can play this little video clip. This animation shows a side view of an area where a river flows into a lake, or any other body of water for that matter. As flowing water enters the body of water, its velocity decreases. The water's ability to carry sediments also decreases. That's its kinetic energy. Sediments carried by the stream are deposited where the slow-moving water can no longer move them. The largest sediments are deposited near the shore. Increasingly smaller sediments settle out farther from the shore where the water is calmer. So we can watch this animation. You'll notice that stream flow slows down, right? The velocity is slowing down. So as it's slowing, larger sediment cannot be carried, so it's dumped out first. This is where sand grains then follow that. So we get large particles, what we call coarse, to sand grains into clay size. And this is called gradation, or this is a sequence of sediment from larger or coarser to smaller that we'll call fine. This animation shows. So rivers and flooding. When we say a river has reached its flood stage, that means it's exceeded its capacity to carry the water itself, or it's exceeded its boundaries. Lag time. Floods do not occur instantaneously. It takes time for water to flow from the land to the body of water, to the river. Flash flooding and urbanization. Remember, urban environments like our suburbs are full of concrete. They are not allowed, they do not infiltrate through the ground, right? Water moving into pore spaces in soil and rock. So it lacks the ability to infiltrate because these are impervious surfaces, right? Impenetrable surfaces, concrete, rooftops, etc. So here's an example. An urban landscape like suburbia. have significantly more impervious surfaces than rural areas. Water does not infiltrate into the ground. Instead, flooding results due to the surge of water moving downhill and towards the rivers or streams and the lakes. We see this as called lag time in the graph. That when we have this heavy event, right, we might have the rapid response. These peaks here would be just because we have rainfall. It's not an instantaneous flooding sequence. So we can have a different rate in which flooding occurs. So here we'd say urban, it might rain at this point right here, but flooding doesn't occur until after some time has taken place. But it's going to be a higher peak because of the impervious surfaces. Whereas this second blip here would be a slower response. This could be like a rural area. Slower surface runoff, more infiltration. So the human response to flooding. There are prevention and barriers. We can dig out rivers so that they're deeper. They can hold more water. Floodplain regulation. Even here at Deerfield High School, we've modified the floodplain. We have flood mapping. We know where flooding is going to take place, so we do not build structures there. We have a deep tunnel project, and that's what we see here. Deep tunnels actually took place locally. Notice this is a deep shaft that's dug down into bedrock. It's dug through the sediment up on the top, and it gives water a place to go. And then lastly, channelization and dredging. That's actually what happened to the Middle Fork River. It's actually just kind of a glorified drainage ditch. So here's a picture of the deep channel, or the deep tunnel itself. That locally in suburbia, when we get a high rain event, heavy downpours, water has somewhere to go. So it doesn't constantly flow into the rivers. It has a place to go. So it's called the Deep Tunnel Project, and this goes through a treatment plant. Well, sometimes the water, when it reaches the capacity and fills the deep tunnel, that water is just allowed to flow directly into rivers, into even Lake Michigan. And that's not good because that takes nasty pathogens with it, including E. coli, which is found in human and animal feces. But what's the problem with that? Well, historically, we just took the chunks out of the water before putting back into the rivers, right? The sewage would enter, even the cleaning facilities. This would be a kind of a simplified version here. But sometimes when it reaches capacity, you're really just putting nasty toilet water back into the rivers. And here's the process that's identified here. Sewage enters, debris are screened and removed, the heavy debris, the larger chunks, and then the grit would settle. That would be removed. That's kind of the next phase here. The sludge settles in the bottom, is removed. They put in microbes to begin breaking and processing the sediment. Then it would have a secondary settling tank, and then lastly the water would be put back. But notice all the microbes, the pathogens of E. coli, are put back in the water itself too. Not a very clean process. However, today UV or ultraviolet light kills the microbes, the E. coli, before being put back into waterways. So a much better system now where ultraviolet light damages the ability for microbes to reproduce, so it actually kills them off. So it's better now, better today. So who cares about flooding? Well, you should. Water leads to tremendous costs, whether to that of your basement that floods or the damage to a community as a whole. You will pay taxes. So therefore you will pay for this in some way down the road. Also, the floodwater that has filled the tunnel network can be released back into waterways and into Lake Michigan. So when flooding events occur, septic water, this E. coli microbial pathogen, can be dumped back into riverways in Lake Michigan. Once it's reached flood stage, it doesn't have anywhere else to go. So we swim in this water, and organisms live in this. Here's a picture that was taken several years ago, looking at the back walkway when we got about 5 inches of rain. And the next day, school was canceled this day. This is the Middle Fork River that's essentially consumed the entire back 40 and all of the athletic fields. So this is a flooding event picture that was taken outside of Exhall.